Good evening, dear students. Okay, today we'll be studying what a register is, and then we will move on to counters. But before that, you need to have a small concept. So let's try to understand what a age-triggered flip-flop is, and then we will move on to registers, right? Age-triggered flip-flop. These are flip-flops which respond at the positive edge or at the negative edge of the clock pulse, that is the applied clock pulse, right? What I mean to say is, we have seen flip-flops synchronized with clock pulse, right? And those flip-flops are active during the active period of the clock pulse. When our CK is equal to 1, that is the entire period our flip-flop stays active, right? Now in case of age-triggered flip-flops, they do not remain active during they do not function in the normal way during the entire active period of the clock pulse, but they stay active only either at the positive edge or at the negative edge of the clock pulse. That means, just a second. That means if a flip-flop gets activated only at the positive edge, that means when the value of the clock pulse changes from 0 to 1, only at this point the flip-flop is active. Those flip-flops are called positive edge triggered flip-flops, right? Similarly, the flip-flops which become active or which function in the normal manner only at the negative edge of this clock pulse, that is when the clock pulse changes from 1 to 0, only at that point of time the flip-flop functions in the normal fashion. Those flip-flops are called negative edge triggered flip-flops, right? Now these flip-flops obviously help to avoid the problem of race around situation, because the active period gets reduced, right? Okay, now so let's look at the logic symbols of the flip-flops which are edge triggered. A JK flip-flop, we know the logic symbol is like this, Q and a Q bar. This is how a normal JK flip-flop symbol looks like. In case of a positive edge triggered flip-flop, we have a triangle over here, right? This triangle at the clock terminal shows it is a positive edge triggered flip-flop, and a triangle with a circle at the end means it is a negative edge triggered flip-flop, right? Okay, so now we can move on to what a register is, because we will be using these edge triggered flip-flops in the construction of registers, right? Okay, so let's try to understand what a register is. As the name suggests, register is something which registers a value, right? So by register in digital electronics, what we mean is it is a group of flip-flops used to store and or move or shift binary, rather use the word shift binary data entered from an external source. Okay, so what a register does is it stores data and also it shifts the binary data that is entered from an external source, right? And it is constructed by a group of flip-flops. In case you want to store a n bit data, you will require n flip-flops. Okay, To visualize this you can think of a calculator. In a calculator, we enter a value and we want that value to be registered. When we enter the second digit, we want the previous digit to shift, right? So that is what happens in a register. We enter a value that gets stored, and as we enter more values, the previous values get shifted and stored. So that is the exact function of a register, right? Now, depending upon the mode of data entry and how we get that out, there are 4 types of register, right? Now the data can be entered all at a time or one at a time. Like in calculator, we enter one data at a time, and the output that we get is in a parallel form. That means we enter a 2, enter a 3, enter a 4, and then we get a 234. That is, we get the output all at a time, but we entered the data serially, right? So depending upon how we enter the data and how we get the result, registers can be classified into 4 types, right? One is serial in, serial out. Second is serial in, parallel out. Third, parallel in, serial out. And fourth, parallel in, parallel out, right? By serial input or serial output, we mean the data are entered or retrieved one at a time, okay? And by parallel in, parallel out, we mean the data has been entered or retrieved all at a time. At a particular instance of time, all the data has been entered, or at a particular instant of time, all the output has been displayed all at a time, okay? So that is what we mean by parallel in or parallel out. So now let's try to see what a serial in, parallel out register is, because that is what we have in our syllabus, okay? Okay, before knowing that, we should know what a shift register is. Shift register, any register in which either the data entry or the data output happens in serial manner is called a shift register, okay? Very soon we will know why it is called a shift register, because our bits get shifted from right to left by the application of clock pulse. That is why whenever our data entry or retrieval process is in serial method, we call it a shift register, right? Okay, so let's look at a serial in, parallel out 4-bit shift register, how it looks and what it does, okay? Serial in, parallel out 4-bit shift register. By the time I draw the circuit of a shift register, please have a look at what a D-type flip-flop is and what a T-type flip-flop is, because we will be using that right now, and also the function of clear and preset in JK flip-flop. That is very important when you try to understand the functioning of a register, right? Since it is a 4-bit register, we will be using 4 flip-flops, right? Just back I have mentioned that the number of bit you want to store is equal to the number of flip-flops you require to construct the register, right? Since we want a 4-bit shift register, we have our 4 flip-flops. The flip-flop we will be using are D flip-flops, serial input, it's better you change the name this to 3. These are 2, these are 1, these are 0. Okay, and we have our clock pulse. We have tied all the clock pulse together. CK. We have all our clear inputs. Sorry. Clear inputs tied together. CR. We have all our PR inputs tied together. PR. This is our clock pulse. CK. CK. Q3, Q3 bar, Q2, Q2 bar, Q1, Q1 bar, Q0, Q0 bar. Okay, so this is a 4-bit shift register, that is a serial in parallel out register, which has been constructed using D-type positive edge triggered flip-flops, right? We can see these are D-type flip-flops and these are positive edge triggered flip-flops, right? This triangle means that. Let's try to understand the functioning. Okay, it is very easy. First, you need to understand what a D-type flip-flop is. In our last class, we have done a D-type flip-flop, right? Over there, we have seen that if in case of a D-type flip-flop, our input and output are, when we have a 0 in the output we get a 0, when we have a 1 in the output we have a 1, right? So like you can see, the value that we enter gets registered. That is what we get in the output. If we give a 0, we get a 0. If we give a 1, we get a 1. So by seeing this truth table, it is very evident that a D-type flip-flop will be used to register values. So that is what has been done. Now please, just a second. Okay. So if we try to understand the working, please try to understand. You did not write now because you have it in your PDF. Say for instance, we want to register a 4-bit data B1001. We want to register this, right? If in this case, this is the most significant bit and this is the least significant bit, right? That means Q3, Q2, Q1 and a Q0. This is the orientation of my 4-bit data, right? What we want to do is we will input these data in a serial manner. By serial manner, I mean I will input one data at a time, and finally I will retrieve the data in a parallel manner. That is, all the 4 values will be displayed in the 4 terminals at a particular instant of time. Right? So if I give all the data, if I input the data one at a time and get the output all at a particular instant of time, all at once together, we can call it a serial in parallel out 4-bit shift register, right? So how it works, we can see. Okay, so the initial functioning is, first we apply CR is equal to 0. On applying CR equal to 0 and PR is equal to 1, what happens? All our outputs Q3 is equal to Q2 is equal to Q1 is equal to Q0 is equal to 0, right? That means we clear all the outputs. We set all the outputs to 0 by our clear input. This is our first step. Our second step is, then we want to return back to the normal functioning. So we apply CR is equal to PR is equal to 1, because we know when this is applied, the flip-flops will function in their normal method. Normal functioning will happen, right? Now we will apply the least significant bit first. That means we will apply Q1 from here. Okay, Q1 is 1, so we will apply Q1. Okay, Now we apply the clock pulse. We give the data that we want to input and then we start the clock pulse, right? What happens? Since this is a positive edge triggered flip-flop, the moment the clock pulse changes from 0 to 1, that is the positive edge of the clock pulse, the moment the clock pulse gets activated, this 1 moves to the output Q3 over here, because the function of a D flip-flop is just shifting the value from input to output by the end of the clock pulse, right? Since it is a positive edge triggered flip-flop, the moment the clock pulse gets active, this 1 shifts from here to here, right? Over here we had a 0, this Q3 is connected over here. That means 1 comes over here, the initial 0 over here goes to here, the 0 over here goes here, and the 0 over here goes here, right? So by the application of the first clock pulse, what happens? The least significant bit arrives at Q3 and the other Q2, Q1, Q0 stays as it is, right? Then what happens? Then we give the second least significant bit, that is 0. We apply 0. Now again, on the application of the clock pulse, this 0 that we have applied gets transferred to Q3. On Q3, previously we had 1, which on application of the clock pulse, it is also applied to this flip-flop. This 1 gets shifted over here. 1 comes over here, right? Over here there was 0, the 0 comes over here, and over here it was 0, the 0 comes over here. That means as we apply the serial input with the application of the clock pulse, they move towards the right, right? On the third step, we again apply this 0. On the application of the clock pulse, again the newly applied 0 comes from the input to output, that is the 0 comes over here. In this place we already had a 0, that 0 transferred comes over here, the 1 over here changes place, reaches here. So by and by, with the application of the clock pulse, our serial inputs gets transferred from one flip-flop to the other. Okay. For better understanding, let's see the reading of the shift register with each clock pulse, if that will help you to understand. Clock pulse, serial input, Q3, Q2, Q1, Q0. One, two, three, 4. Our serial input was 1001. Initially all these values were 0. Okay, I'm drawing it over here for your convenience again. I'm not drawing the entire picture, I will just draw the serial input, this is the D3, Q3, D2, Q2, 1, Q1, D0, Q0, and this is our clock pulse. I'm not drawing the rest of the diagram, I'm just drawing this so that you can understand. First we have all these values equal to 0, 0, 0, 0. This we have done by applying clear is equal to 0, right? Now what happens, we have changed the clear and peer to 1 in our second step so that the flip-flops function normally. Now we apply the first value, that is the least significant bit, 1 over here. Okay, on the application of the clock pulse, what happens? So these were the values that we already have. Okay, that is 0, 0, 0, 0. On the application of the clock pulse, what happens? This 1 immediately comes over here. That means the Q3 displays a 1. Okay, Over here we had a 0, this 0 gets transferred over here, that means Q2 displays a 0. In Q2 previously there was a 0, that immediately gets transferred over here, so Q1 displays a 0. On Q1 we had a 0 that immediately gets transferred over here, that means Q0 displays a 0. Since all are connected to clocks, these all flip-flops get active at the same time, at the same instant, right? So now our present scenario is we have a 1 over here, a 0 over here, a 0 over here, and a 0 over here, right? This is our present scenario. Now second, we apply our second beat, that is 0. The moment we apply this 0 and the clock pulse gets active, this 0 gets transferred over here, right? That means this 0 comes in Q3. Over here we had 1, so immediately that 1 gets transferred over here, that means we get a 1 over here. In Q2 we had 0 stored in the earlier stage, so that 0 gets transferred to Q1, so we have a 0 over here. And again we had a 0 in Q1 in the earlier stage, that gets transferred to Q0, so we get a 0 over here, right? This is our scenario by the end of the second clock pulse. Okay, now we want to input our third digit, that is a 0, so in the serial input we give our 0. On the application of the third clock pulse, what happens? This 0, that is a new 0, gets shifted to Q3. That means this 0 gets shifted to Q3. In Q3, in the previous step, we had this 0, right? That 0 gets shifted to Q2. That means this 0 gets shifted to Q2. In Q2, in the previous step, we had 1. So on the application of the clock pulse, this 1 gets shifted to Q1. This 1 gets shifted to Q1, right? And in the previous step we had a 0 in Q1, that 0 gets transferred to Q0, that means we have a 0 over here by the end of the third clock pulse, right? So our present scenario is 0 0 1 0. Now before the fourth clock pulse we put our last entry, that is 1. We are giving one entry at a time. Okay, so that is our serial input. On the moment we apply our fourth clock pulse, what happens? This 1 gets transferred over here, that means in Q3 we get this 1. The 0, that is a Q3 in our previous step, gets transferred to Q2, that is the 0 comes over here. The 0 of Q2 in the previous step gets transferred to Q1, that is we get a 0 over here in place of Q1. And the 1 in Q1 in the previous step gets transferred to Q0, so we get a 1 over here, right? So by the end of the fourth clock pulse, just see the output that we get. It is what we wanted to store, 1001. After the fourth clock pulse, we have to stop the clock pulse because else our data will keep on changing. So the number of bits you want to store is equal to the number of clock pulse you apply. So since we want to store 4 bits, we have to apply only 4 clock pulse. By the end of the 4 clock pulse, we can get our output in a parallel form, that is these will get displayed all together at a particular time. So we had entered our data in serial manner, but we retrieve the output in a parallel manner. Okay, so this is the total working of a shift register, that is a serial in parallel out shift register. So this entire circuit that we have made are using we constructed it using D-type flip-flop. Your homework will be to construct a 4-bit serial in parallel out shift register using JK flip-flop. This is your homework. And okay, before wrapping up, I would like to show you the logic symbol of a serial in parallel out 4-bit shift register. The logic symbol is like this. When you are making it with a D type flip-flop, your logic symbol is like this: serial input, we have the clock pulse, and we have our output all at a time: Q3, Q2, Q0, Q1. Okay, so that's all. Okay, just remember that when you enter your data in a serial in parallel out shift register, we enter the least significant bit first, and that keeps on moving, and finally the last step we enter the most significant bit, right? Then our data gets displayed in the proper manner. Okay, so the next day we could not complete today. The next day we will see what counter means. So please try to understand it, and in case you have any confusion, do let me know. Thank you.